let's keep going. I know everyone's getting hungry for lunch. We got our next presentation coming up. We have Anton McGonnell, who's the head of product at SambaNova. Please welcome Anton to the stage.
Am I on? Do I talk? Okay. Hello. A lot of people. Following up a race car presentation. See how this goes. Okay. Right. Anton McGonnell. I work for a company called SambaNova. SambaNova is a full-stack AI company. We make chips, we make systems, we make racks. We have our own software stack. And we take the best of the open source models and optimize them to run efficiently in our systems for both training and inference. And what I'm talking about specifically today is a concept that we call composition of experts, and we'll dive into what that means and why it is, in our view, a fundamentally better approach, and why our systems are particularly well suited to this type of architecture. So, two trends that I think are starting to unfold and are somewhat indisputable at this point. The first of which is bigger is better as it pertains to large language models, transformers. OpenAI's GPT-4 is, by all accounts, probably the largest closed source model there is at 1.8 trillion parameters. And broadly considered the best, both from a qualitative and quantitative standpoint, the best model available today. Then we have Falcon 180 billion parameter model, which is top of most of the leaderboards today on the open source model benchmarks, and it is the largest open source parameter model available today. So the problem with this is, if bigger is truly better, which it seems it is, then how do we scale these models up, given that it's extremely expensive and costly to train these models, and it's also just becomes very, very unstable to run training jobs on really, really large parameter count models. And it's even more costly to serve for inference. It's just unsustainable to run these trillions of parameter dense monolithic models at scale. And it's also, the maintenance of these models obviously becomes a serious bottleneck as well, because every time you train or fine-tune the model, it takes lots and lots and lots of time and isn't particularly modular or extensible. The second trend is that LLMs are really good at doing one task at a time. So if you ask GPT-4, for instance, a very complex multi-step question, it doesn't do as well as if you break that down into composite parts, one step at a time, ask it the first part of the question, then take the output of that question and feed that in as the next part of the question. And this has caused a rise of these application frameworks like LangChain and LlamaIndex and semantic kernel that allow you to compose these workflows where I make this request and I get the output of that request and I use that as the input to this request, and I can go to one model, I can go to lots of models, I can go to models plus embedded knowledge within vector databases, etc. So these are the two trends we're seeing. Now, SambaNova, as I said, we're a full stack platform, and underlying that platform is our chip called the reconfigurable data flow unit. So this is, we're 6 years old now. The company was founded in 2017. It was research incubated in Stanford University in California. And the fundamental belief is that there is a better approach to AI acceleration using data flow. And the key, and this, by the way, is a chip we just announced several weeks ago. It's the 4th generation of our chip. And the real innovation for us is this 3-tier memory architecture. So we have really, really big, high-capacity DRAM. There's 8 sockets on a single system. And so you see 1.5 terabytes. Does this work? Yeah. You see 1.5 terabytes high-capacity memory here. You multiply that by 8 at the system level. Goodness. Multiply that by 8 at the system level. Then you have this intermediary memory, high-bandwidth memory. Again, you multiply that by 8. And then you have the on-chip SRAM, which allows you to do this data flow. You're able to map spatial problems. You're able to map things sequentially as opposed to just pure brute force parallelization that GPUs do. And the reason, so if we come back to those two trends that we're seeing, the reason that we have a really, really large advantage is that we have this really big directly connected memory, our DDR memory, which at the system level is 12 terabytes. So that means you can store 5 trillion parameters on a single node. That 5 trillion parameters can come from one single model, or it can be broken into lots of different models or a mix of both. But it cumulatively adds up to 5 trillion parameters that you're able to run on our system. Then we have the intermediary, very, very fast adjacent HBM memory. And we have the on-chip memory. And what our compiler allows us to do is sparsely activate workloads, models, parts of models, layers of models between these two memories really, really dynamically. So being able to run inference at really, really large scale, we've always been very strong in training, always very competitive. Have better training numbers on average than NVIDIA's DGX systems. But the real innovation we have with the SN40L, with our new chip, is just how we can do inference at massive, massive scale and much lower total cost of ownership. And if you look at how GPU systems, for the practitioners in the room in particular, if you think about how you deploy models, typically, most people use containers today and Kubernetes, and you'll schedule a container that's running your model with some web service front end to inference against. You'll load that into, Kubernetes will load that into memory and reserve the compute, the chips, the GPUs for that container, for that model. And so if you want to be able to share that capacity, that computation, you're not really able to with this approach, because each model has its own reserved compute, and only that model can access that reserved compute. So for instance, if you wanted to run 8 small models, or you wanted to run 10 small models, sorry, on a DGX, it only has 8 sockets, so you need to get 2 nodes. With our approach, we do it fundamentally differently now, because we're just taking all of these models and we're running them as one sort of single runtime, loading that into memory, and then a user just is able to declaratively ask which model it wants to run inference against. So think of this in a single system. You can run, in some cases, hundreds, in some cases, thousands of models on a single system with no performance degradation. And for those who are interested in seeing a demonstration of this, come to our booth. It's A26. And so this leads us to this concept of composition of experts. So we are running all of these models. Imagine Hugging Face at the minute, I think there is nearly 3,000 versions of Llama 7 billion on Hugging Face right now, and varying degrees of quality, obviously, but there's a lot of really, really good fine-tuned models available in the open source community today. And they've been adapted either for new domains, new languages, or aligned to do really well at new tasks. But just imagine you're able to run all of those models, or in our case, 700 of them on a single node. So then how are you interacting with those models? And this is what brings us to this concept of composition of experts. So the composition of experts is just a system that runs all of these experts, and we're defining experts as as independent models that have been tuned to do some particular thing. And then how you compose them is through this routing module. The routing module can manifest itself in multiple different ways, but you think of a request coming in, the routing module decides which model expert it's going to load, and then we load that, and that's what you're running inference against. And this is all happening in real time. So in the case of rules-based routing, and you can think of this in the context of a lang chain, for instance. I'm going to compose a workflow where I'm using 5 different models. And I know what those models are. I know what problem I'm trying to solve. Maybe I'm trying to load documents. I'm trying to interpret information from different parts of that document, and I'm using different experts to do so. Maybe I have some graphs or tables embedded within the document, so I need to be able to handle multimodal inputs. And so I know my 5 experts, and I construct a workflow to be able to be able to use them effectively for the problem I'm trying to solve. So in this case, your routing is being done by that lang chain, and that is a much more efficient way to solve that problem than using one really, really, really big monolithic model to do all of those 5 things. The other approach is intelligent routing. So again, imagine these 700 llamas just sitting there, ready to be used in any way you want them to be used. Well, you can actually just train another model to act as a classifier, so that when a request comes in, you're able to, this routing model is able to choose the appropriate expert to solve that problem that you're asking it to solve, or n number of experts to solve the problem that you're trying to solve. So these are 2 ways to compose experts: a rules-based deterministic approach and an intelligent ML probabilistic-based approach. And the value of this composition of experts approach in terms of real tangible business value is, number one, it results in a much, much better total cost of ownership for inference. So if you think of running 5 trillion parameters and up to 256K sequence length, which is another benefit of our very sophisticated memory architecture, you can do that on a single node at 300 tokens per second, assuming that you're using, the 7 billion as the form factor for each expert. So from a TCO perspective, there's no equivalent to do that. The only other way is to buy lots and lots and lots of DGX systems. It's also incredibly modular, so you can train expert by expert. It's extensible. You scale up the total parameter count over time, as opposed to starting with this really, really big, large model. It avoids the alignment tax problem, so as you fine-tune new experts, you're not degrading performance or accuracy on previously trained domains or tasks. And it enables this very granular access control. So again, if you think of one large monolithic model, it's very, very difficult to say people in HR shouldn't see finance information, people in finance shouldn't see HR information, because they're all interacting with one monolithic model, and it's very, very, very hard to determine who can see what. So with this approach, you're able to define access control at a very granular level, and only some subset of people within your organization get access to some subset of experts. So that is it. I'm not going to do that slide. That is it. So we're super excited about this. Composition of experts is a fundamentally new approach that we think is a better approach. It's not just us saying that. Others, including Hugging Face, including many of the thought leaders in this space, are saying the same thing in a different way. And it just so happens that our system and architecture is uniquely positioned to do this stuff at really, really big scale, and we're super excited. So if you want to see demos or you want more information, come to our booth. It's like if you go out here and you come to the robot dog and you go left, and it's there. Thank you very much.
Thanks, Anton. That was super impressive. We have a little bit of time for questions. Anyone in the audience? Yes, sir. Right up here at the front.
Great talk.
Thank you.
So speculative question. Have you guys thought at all about how this general approach of composition of experts might be a path towards artificial general intelligence, where you have many different domain experts, but they sort of integrate together in an overall sort of general intelligence?
Yeah. I mean, if you think about it, it's not fundamentally different to like, right. I think it depends. If you assume that general AGI will be solved by purely autoregressive models, then there is no reason that this approach is certainly worse. It may actually be better than just really, really, really large dense models, because really large dense models, whenever you're using them, you're only, for each request, activating a tiny subset of the weights of the model based on whatever task you're trying to solve. So in that sense, being able to better modularize expertise and understand what task a user is trying to solve, and making sure that you have the right number of experts and the right experts and the right number of experts to solve that particular problem. I think regardless of whether you use the dense approach or you use the sparse approach that we're talking about, this approach may be better, but I'm not sure that either way is enough for AGI.
Thanks very much. Any other questions from the audience? Hands up. No one? Anton, I have one more question for you. Can you elaborate a little bit on how the composition of experts technique differs from previous techniques like mixture of experts?
Yeah, okay, yeah. And so mixture of experts, I mean, GPT-4 is a mixture of experts, 16 experts, which is not very granular. So unclear whether it's really utilizing the concept of mixture of experts well. But the difference is mixture of experts is just one model. Mixture of experts, like switch transformer, I think is probably the most popular mixture of experts architecture today, and it just splits the model, the expertise with the layers of the model. But it still faces the same fundamental limitations in that you can't train those layers independently. You need to train it all together. So as you scale it up, you still have those really high costs for training. It also doesn't allow you to do this granular access control, because the experts emerge. The experts aren't defined. Like it's not an expert in finance, an expert in HR. It's just via the training process. It will the difference between expert A and expert B will just emerge. So it's not particularly enterprise ready. And it's also just harder to decompose in a way that allows you to get the benefits of sparse activation, only loading the parts that you really need for each prediction request. So I think mixture of experts has been an approach to solve the problems that we're addressing here. It just doesn't seem like it's the best one, and that's why this approach of composition of experts, where you have independent models acting as experts, we believe is a better one. And we're calling it composition of experts, but we're not the only ones saying this. It's just that we're the only ones calling it that.
Gotcha. One more minute. Time for one last question, anyone? There's a gentleman over here. Do we have a microphone? It's okay if you want to shout it, I'll repeat it. Go ahead.
Yeah.
Hardware stack or software stack.
Yeah.
So on, do the same thing on your hardware.
Yeah, so we have our own compiler and runtime and software because we need to, because it's a fundamentally different architecture. So you can't just use CUDA on our system. That's called SambaFlow, and you're able to write new operators, for instance, using SambaFlow. But you don't actually need to, because we do automatic kernel fusion and these sorts of things. So you just operate at the PyTorch level and build your model, and it'll automatically compile and scale out. And we just ship all of the models pre-compiled out of the box anyway. So given that the world is very much data-centric AI is much more prevalent, model-centric AI, by virtue of that, you don't even need to interact with PyTorch. You just tune the hyperparameters, bring your data, and train the model.
Give Anton a big thanks. Round of applause.
Thank you very much.
Cheers, Anton.